Welcome to our thermodynamic class. I'm Yushazana and my partner Nurin Zulaika. A refrigerator or heat pump that operates on the reverse Carnot cycle is called a Carnot refrigerator or a Carnot heat pump. For a refrigerator, we are interested in how much heat is removed from the core reservoir for a given amount of work by outside forces on the system. For a heat pump, we are interested in how much heat is delivered for a given amount of work done by outside forces on the system. What is reverse Carnot cycle? As name indicates, the cycle having reverse direction, that is anti-clockwise direction like this. We see from the block diagram, heat QL is absorbed from the low temperature reservoir, TL equals constant, and heat QH is rejected to a high temperature reservoir, TH equals constant. The reverse Carnot cycle also consists of two isentropic, 2 to 3 and 4 to 1, and two isothermal process, 1 to 2 and 3 to 4. The process undergoes in direction 1, 2, 3, 4, 1. Process in reverse Carnot cycle consists of process 1 to 2, absorption of heat by the working fluid from refrigerator at constant low temperature TL during isothermal expansion. Process 2 to 3, isentropic compression of the working fluid with the aid of external work. The temperature of the fluid rises from TL to TH. Process 3 to 4, isothermal compression of the working fluid during which heat is rejected at constant high temperature TH. Process 4 to 1, isentropic expansion of the working fluid. The temperature of the working fluid falls from TH to TL. Practically, the reverse Carnot cycle cannot be used for refrigeration purpose as the isentropic process requires very high speed operation, whereas the isothermal process requires very low speed operation. This is the coefficient of performance relations for reversible refrigerator and heat pumps. These are the highest COP that a refrigerator and heat pump operating within the temperature limits of TL and TH can have, while actual refrigerator or heat pump operating within these temperature limits have lower COP than the reversible. Carnot principle applied to a refrigerator. The coefficient of performance, COP of a refrigerator or heat pump, is always greater than the COP of irreversible process operating within the same high and low temperature reservoir, regardless of type of devices, working fluid, and etc. The COPs of all reversible refrigerator or heat pump operating within the same high and low temperature reservoir are always equal. The coefficient of performance of actual and reversible refrigerators operating within the same temperature limits can be compared like this. For heat pump, we can replace all COPRs in the comparison with COPHP. Now, we move to the example. Make its explanation more clear. For example 1, reversible refrigerator have maximum and minimum temperature in the cycles 27 degrees Celsius and negative 3 degrees Celsius respectively. We can insert the temperature in any of these three equations. We must insert temperatures in unit of Kelvin. So, we get the COP of Carnot refrigerator is 9. Now, we have to calculate for actual refrigerator with the heat given. Here have example for three situations with different QH and QL. For situation 1, value of COPR are less than COP of Carnot refrigerator. So, these refrigerators are classified as irreversible refrigerator. For situation 2, value of COPR are equal with COP of Carnot refrigerator. The refrigerators are classified as reversible refrigerator. For situation 3, value of COPR are more than COP of Carnot refrigerator. The refrigerators are classified as impossible refrigerator. For heat pump, the comparison also same with refrigerator. The difference only the equations. The coefficient of performance of a reversible refrigerator or heat pump is the maximum theoretical value for the specific temperature limits. Actual refrigerator or heat pump may approach this value as their design are improved, but they never can reach them. All actual processes are irreversible, hence completely reversible cycles are idealization only and cannot be used in practice. Reversible cycle is used as a reference or a standard to compare the actual cycle, that is to check how good is our actual cycle with the best possible cycle. But why actual cannot be ideal? This is irreversible factors. The factors that cause a process to be irreversible are called irreversibilities. They include heat transfer to a finite temperature difference, unrestrained expansion of a gas, mixing of two gases, friction, electric current flow through a resistor, inelastic deformation, and chemical reaction. The process is irreversible if any of these effects present.
What is the method to maintain the highest COP refrigerator and COP heat pump for the actual device? The coefficient of performance of a refrigerator is defined as the heat removed from the core reservoir divided by the work done to remove the heat. As can be seen, the more efficient refrigerator is when more heat Q cold can be removed from the inside of the refrigerator for a given amount of work. Ideal refrigerator can be derived that COP equals to T cold over T hot minus T cold. COP of the heat pump is the ratio of the heat added to the system. Can be defined as the heat removed from the core reservoir plus the input work to the input work. COP of heat pump can be improved by reducing the temperature difference. Reducing the output temperature is very efficient but requires very efficient heat transfer from the heat pump system to the surrounding. The example is use of pipe floor. Next, the example for an increase in the input temperature is an oversized ground source of heat. The ideal heat pump can be derived that COP heatings equals to T hot over T hot minus T cold. What is the technology that can improve the energy saving and preserve the environment? One way is by using a renewable energy resource to fuel our system and produce the work that we need. Solar energy is a great example. Rather than taking electricity that was made from a typical source, we can use solar power photovoltaic panels to convert the sun's ray into electricity by exciting the electrons within the panel cells. The electricity that we get from this energy could replace the work that we need for the cycle, that making the cycle itself more usable. The amount of energy consumed by refrigerator can be minimized by practicing good conservation measures. First, open the refrigerator door the fewest time possible for the shortest duration possible. Keeping the refrigerator off freezer full will save energy by reducing the amount of cold air that can escape each time the door is opened. Second, cool the hot foods to room temperature first before putting them into the refrigerator. It will make the refrigerator work longer. Third, clean the condenser coils located behind or beneath the refrigerator. It will improve the cooling ability of the refrigerator while cutting down the power consumption by a few percent. Fourth, check the door gasket for air leaks. Heat transfer through the door gasket region accounts for almost one-third of the regular heat loss of refrigerator, and thus any defective door gasket must be repaired immediately. Fifth, avoid unnecessarily low temperature settings. Keeping temperature 6 degrees below recommended levels can increase energy use by as much as 25%. 6. Avoid excessive ice build-up on the interior surface of the evaporator. 7. Use the power saver switch that controls the heat coils and prevent the condension on the outside surface in humid environment. 8. Do not block the airflow passage to and from the condenser coils of the refrigerator.